So this is lecture 19 of problem solving. I apologize for the technical failure where I was relating a story of some voting shenanigans in the past. So sorry that this did not record. But I have passed out some thoughts on a modification to the voting procedure for national organization. The last time they used the current voting procedure, it took them 6 ballots to finish their election. This is not bad as some presidential elections, which have gone to over 30 ballots, but still 6 is significantly more than people want. And so one of the goals, this is a problem-solving class. Let's try to take what we've learned and look at some real problems from the world. And so you will be asked to analyze the procedure that I am suggesting as to, do you think that this is fair? What do you think the issues might be in implementing it? Do you have another idea of what might be a good suggestion, a good thing to do? And then part of this will be not just a theoretical exercise, but also simulating. And so, in an ideal world, we would actually have huge numbers of people and just have them vote. We can try to come up with what we might think are reasonable voter profiles and see what kind of results we have. Maybe 95% of the time, we finish in 3 ballots or less. Something like that to get a sense. And then you could look at some other systems. And then this way you would have a rough idea of the possibilities. OK, so what I want to do now is go back to integration. So there is a lot of stuff to do in integration. We had the baseball lecture on Monday in honor of the start of the season. Although looking outside, you wouldn't realize that this is spring. Why do we care about integrals? Or at least what's one good reason why we care about integrals? Probability. Right? And this is why there's an entire class devoted to probability. And because we have better techniques for integration than summation, we often like to do things with continuous things. So integrals are important. So here is a nice integral. Integral from 0 to infinity. Let's do x over x dx. So what's the first thing you should do whenever you see an integral? Yeah, do you converge? It says yes, it does. So good. So you always ask, does it converge? So what are the dangers? So whenever you have an integral, what are the dangers that could stop convergence?
Discontinuity?
So discontinuity. If the function is discontinuous enough, the Riemann integral is not going to converge. This function is at least continuous. What else do we have to be careful about? Yes?
If the integral starts at 0, if the thing blows up at 0.
Well, if it blows up anywhere.
Or if it blows up.
So does the integral blow up anywhere? So the only danger point for blow up is x equals 0. Right? So we have to be careful, does it blow up? So we need to check x equals 0. So take the limit as x goes to 0 of sine of x over x. All right, how do we compute this limit? What do we use? L'Hopital. And what's the derivative of sine? Cosine of x. And what's the derivative of x? And so cosine of 0 is? All right, everybody comfortable with this argument? Does anybody have concerns with this argument? Everybody's comfortable doing calculations like this. You all fail. What did you do wrong? It's really subtle. It's one of my favorite things to emphasize about how it's so easy to slip things past people. OK, how do we get from this step to this step? What do we use? L'Hopital. And when we got the derivative of sine as cosine, how do we do that?
We know the derivative.
How do you know the derivative of sine as cosine?
From sine.
Limit as h goes to 0 of the sine of h plus 0 minus the sine of 0 over h. What's the sine of 0? 0. So this is just the sine of h over h. I'm changing letters. Right? You can't use L'Hopital Or if you're using L'Hopital, you already know the answer because you're saying the derivative of sine is cosine. So in order to use L'Hopital here, you somehow have to already know this limit. So this is one of the most important limits in mathematics, the limit of sine of x over x. So there's a lot of different ways you could prove that this limit is equal to 1. You could look at circles and your inscribed gons and look at areas and perimeters. It's converging to the area or the perimeter of the circle, and you can use that to get that sine of x over x is going to 1. You could, if you know sine of x's Taylor expansion, you could get it from that. But you do need to somehow know this is one of the most important limits. If people want, I'm happy to do a digression on trigonometry and limits like this. I'm also happy not to. This is personal control. So if anybody wants to see how you calculate these limits, let me know. If not, I'll just say the limit of sine of x over x is 1, but that's something you have to know. Okay, so you just have to know, looking at areas of circles, that's a great way to get it. So when we check x equals 0, we're fine. Now, the problem is, as we go off to infinity, it's decaying, which is good. If it wasn't decaying, we know the limit wouldn't exist. So there's at least a chance because it has decay. The problem is, it's not an L1. And so we say f is an L1 of here, our space would be 0, infinity. Oops. If the integral from 0 to infinity of the absolute value of f of x dx is finite. And unfortunately, if we put in absolute values, this will diverge to plus infinity. And the reason is, sine of x is going to be 1 fairly often. Basically every time you increase by, 2 pi. And if you move a small fixed amount to the left and right of it, it's not going to really change that much. You can basically show that this is an absolute value. The integral is going to be greater than or equal to some constant times the harmonic series. So as a nice exercise, you should show that the absolute value of this function is plus infinity. What this means is we have to be careful. And whenever you have something which is not an L1, it can matter how you integrate. So one of my favorite examples is if you integrate the function x, 1 over 1 plus x squared dx from negative a to a, and take the limit as a goes to infinity, what do you get? You should get this very fast. 0. Why is it 0? Yeah, this is an odd function on a symmetric region. So the integral is just 0. But if I went from negative a to 2a, then this would be the same as the limit as a goes to infinity, the integral from a to 2a of x over 1 plus x squared dx. And this integral here is essentially, the integrand is essentially 1 over x when x is large. If you want, it's greater than or equal to 1 over 2x from a to 2a dx. Take the limit as a goes to infinity. And then that's going to be your natural log. Now you get the natural log of 2a minus the natural log of a. So you get like the natural log of, I think, 2 over 2. So this integral, its value depends on how you go to infinity. If I go to infinity in a symmetric way, the integral is 0. If I go in a way that's biasing the positives over the negatives, I can actually get anything I want. And we could calculate exactly what this is, because as you were saying, you noticed that the top is essentially the derivative of the bottom. We could get the exact answer, but it's enough to just show that it's not 0. So we have to be careful. This integral, it's not immediately clear that this integral makes sense. So what could we do to justify that this does integrate to a finite number? Yes? Good.
and say that initially you first have a positive from 0 to pi.
Right.
And then you have a negative, and then you have a positive and negative. And the area under all of this, the absolute value of each period is always going to be decreasing.
Good.
So if you start with the positive, you can cancel out the first with the second, the third with the fourth, and so on. And it'll be positive. But then if you take out the positive, you can cancel out the second with the third, and so on. And it'll be a positive plus some value that's
Excellent, excellent. So we're going to just march down as was remarked, and in each one, the absolute value of the integral is smaller than the previous, because the top parts are going to go through the same oscillation, but the bottoms are going to be smaller. And so this is an alternating series. Actually, it's better. It's an alternating decreasing series. Therefore, it converges. So the integral at least makes sense and it's well defined. So then the question becomes, how do we actually evaluate the sine of x over x? What would you love to have for this? So in Calc 2, you always have this. Any problem in Calc 2, you always have this. So when I give you an integral in Calc 2, what do you have?
integration technique that works.
An integration technique that works. And so what does the integration technique give you? Given a function,
Closed form.
it gives you a closed form answer. It gives you an antiderivative. So we want a function whose derivative is sine of x over x.
Could we do some sort of whatever the inverse product rule is like?
I'm sorry?
Integration by parts. Can we do that?
So we could try integration by parts. So we have u and dv. Do you want u to be sine of x or 1 over x?
Probably sine of x, because you probably don't want the 1 over x to keep on being derived.
Okay, but then if you have 1 over x being the dv, you're going to get a natural log. So unfortunately, integration by parts, it's a nice thing to try. It's one of our few techniques. It's not going to work well. We could try a series expansion. The problem with the series expansion is the sine of x. So, big series expansions, e to the x is the sum, n goes from 0 to infinity. It's a terrible infinity. X to the n over n factorial. Sine of x is the sum, n goes from 1 to infinity of negative 1 to the n plus 1 x to the 2n. Maybe I want to and it's 0. I'll do it this way. So this is just going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Now what's nice is this series converges for any choice of x. But if I were to integrate this, if I try to interchange the sum and the integral, I'm now integrating x to a power from 0 to infinity. That's going to blow up. And I'll have basically infinity minus infinity plus infinity minus infinity. Okay. And then just for completeness, cosine of x is the sum, n goes from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus ... So these are some of the classic series expansions. We can't do a series expansion here. A series expansion is not going to help us. There are some great techniques. How many of you have done complex analysis? No one has done complex analysis. Well, this gives us an interesting possibility. The most important part of complex analysis is to convert integrals to finding a Taylor coefficient. In fact, finding the negative first Taylor coefficient of a function. And if you can do that, you can actually convert a lot of integrals to just algebra. And this is one of the powers of complex analysis. So if people want, I can actually teach you the complex analysis to do these integrals. I can't teach you why it works in great generality, because that requires maybe 2 weeks of complex analysis. That's too much of a detour. However, I can promise that there will be a complex analysis class next year, and so if you want to see why it works, I can show you why it works for some simple cases, and then we just put on our engineering hat and say, we can switch these things, we can approximate these things, and I'll show you how we can actually evaluate these. So one thing, so do people want to see complex? All right, so, all right, there we go. Okay, so, you know, limit of sine of x over x. Complex, yeah, let's see. Okay, so we'll do complex. So I'm going to just put something in the bank right now for complex. I'm going to show you how to set things up. So the integral from 0 to infinity of sine of x over x dx, this is the same as 1/2 the integral from minus infinity to infinity sine of x over x dx. And the reason is sine of x over x is even. Okay? This is the same as 1/2 the integral from minus infinity to infinity of sine of x. I want to do this. Let me just think for 1 second if I want to do it this way. Yeah, I'll do it this way. So you should be a little bit concerned because the absolute value of cosine of x over x blows up, but cosine of x over x is an odd function. And so if I interpret this integral as I'm doing things from, say, minus a to a symmetrically and expanding, do we agree that this is okay? So what I would have to do is go like this.
Why doesn't cosine x over x blow up at 0?
Okay, so I have to be careful. Yes, okay, that's right. I've got to be very careful here. Thank you. So what I need to do, thank you, is minus a to epsilon to minus epsilon plus epsilon to a. Thank you.
As epsilon.
Epsilon's like arbitrarily.
And epsilon goes to 0 and a goes to infinity. Yes, thank you. I have to be very careful and I have to do it like this. Then if 1 is the same as I to the 4th. So this is the same as, I'm going to pull out a minus I over 2, limit as a goes to infinity, epsilon goes to 0, integral minus a to minus epsilon, integral epsilon to a, and then this is cosine x plus I sine of x over x dx. Well, what's cosine plus I sine?
That's e to the...
Yeah, this is just e to the ix. And so you can convert it to doing an integral like this. And then in complex, instead of using the letter x, we like to use the letter z. And so this is integrating along almost a line on the real axis. So the region of integration is going to look like this. And these 2 points are getting closer to each other, and these 2 points are going to go off to infinity. And what we're going to do is, this is how we're doing the integration. We're going to add a little circle like this and a circle like this. And we're going to have a nice closed curve. And we're going to integrate this function over the boundary of a closed curve. Does that remind you of anything? What does it remind you of? I'm praying right now that you remember something from previous math classes. We're integrating a function along the boundary of a closed curve. What theorem does this remind you of? I'm sorry, Green's theorem, Stokes' theorem, something like that. So we actually have results like that available. And the whole point about Green's theorem and Stokes' theorem is you can often convert a line integral to an area integral or something like that, and you can often get really nice answers. And so we will find a technique that will allow us to do this with complex analysis. And the answer is very clean. Yes?
I'm just a little confused how you got from the line 1/2 integral negative infinity sine x over x into sine x minus 1. Like, where'd you get the minus I cosine x?
Well, his thing is cosine x over x is odd.
Right.
And so if I integrate an odd function over a symmetric region, it's 0.
Oh, okay. Okay.
And as was remarked, I've got to be very careful because it does blow up at 0. So I have to stop at minus epsilon and then start again at epsilon. And so the whole point is we're adding 0 in a clever way. And so I will show you how to do all this stuff using complex analysis. It's a really nice detour, and it converts a lot of these integrals to just algebra. And you might remember from Stokes' theorem or Green's theorem that maybe your function blows up at a point. And then if it blows up at a point, what you do is you do like the small little detour around that point. That's all of complex analysis.
Can you explain the whole picture?
We're gonna spend more time on this, but I'm saying the integral we're doing here is just the integral over this segment here and this segment here. What I do is I add 2 semicircles to complete. And then what we'll show is that the integral over this closed curve is the same as something nice with the interior region. And then it turns out it's actually very easy to integrate over the 2 semicircles. And that's where everything is going to come from. So this is, yes?
How did we get from 1/2, limit 1/2 to pulling out negative I?
So 1 sine of x is the same as I to the 4th sine of x. Right? I to the 4th is 1. Negative I is I cubed. So I pull out a minus I, and that leaves. This is why you might have seen me, and you can actually watch the video. You can see me pause for a second. What do I want in front of cosine? Do I want an I cosine or minus I cosine? I want minus I cosine so I can get it like this. So we'll see how to actually evaluate stuff like this with complex analysis. But that doesn't really help us right now. And the other thing is that might feel like cheating. Now, I'm a number theorist. We do this all the time. There's a great result or a great quote that often the fastest way to prove a theorem about real numbers is through the complex plane. That when you take this detour into the complex plane, you have a lot of tools at your disposal. But it feels a little bit wrong to be resorting to complex analysis, to be integrating this real function. It's a powerful technique. So there's another thing we can do. Let's look at g of t is the integral from 0 to infinity of sine of x over x e to the minus tx dx. Pretty sure this is how I want to phrase it. Yes. No. I want to do. I might want to do it slightly differently. No, I'll do it this way. This is fine. What do you think about this function? Do you like this function? I mean, would you like to introduce this function to your friends who are taking calculus classes right now? No? Do you have to worry at least if this function is well defined? Is this integral, is it going to exist? So for what values of t will the integral be fine?
1 or greater.
I think you can do a little bit better than 1 or greater. You're close. Okay, if t is greater than 0. And the reason it's okay is you have exponential decay.
Or greater than or equal to 0.
Right, and so if it's actually equal to 0, it reduces to what we have here and we're okay. So we'll all write it's really okay if t is greater than 0. Okay if t is greater than or equal to 0. What would you like to do to this function?
If you take the derivative with respect to t.
Excellent. I was about to say, what if I rewrite it with a capital G? If I were to rewrite it with a capital G, would that make you more likely to differentiate it?
Yeah.
Right? So this is a really interesting question in terms of how you process math and how you come up with what to do. Does the way I present this math? In an ideal world, or if I really cared, what I would do is I would actually have you all come together again, do this lecture, and have like the people in Swarthmore watch a different version where I start off with a capital G and see if they're more likely to think that you should differentiate this. Does it matter how you present material? If I have a little g, or if I have a capital G, if you see the capital G, does that make you more likely to want to take the derivative? And so I have this kind of nice transform. And so for any value of t, I have a new function. The idea is maybe I can come up with a closed form expression for big G. And then what value of t should I choose? So what value of t would I want to choose if I could understand this? 0. And just t equals 0 corresponds to the original function. This is just t equals 0. Does this remind you of any concept we've seen in this class? I'm sorry? Generating functions. This is really similar to generating functions. It's the same idea. I take the thing I want to understand, and I build up this new global object. And then the idea is to try to deduce information about the local information, the t equals 0 piece, from this global object. All right, so let's take the derivative of g. Okay, how many of you have taken real analysis? How many of you have not taken real analysis? Okay. So if you haven't taken real analysis, you're probably in the same boat as those who have taken real analysis, because I doubt you've proven the following theorem. But have you proven a theorem about when you can interchange a derivative and an integral? No, okay. So you have to justify interchanging a derivative and an integral. We want to take the derivative with respect to t. We'd love to put the derivative with respect to t inside. Right? And then when we take, so let's say we can do that. So we need to justify this, and we'll talk about justifying that in a moment. Well, the derivative of sine of x over x with respect to t is not a problem. This is a constant with respect to t. So I need to just take the derivative of e to the negative tx. So what do I get when I take the derivative of e to the negative tx with respect to t? Negative x. All right, so now we want to integrate negative sine of x times e to the negative tx. Can we integrate this? Really hope so, otherwise this is a bad lecture.
Yeah, we could use the integration by parts.
Yeah.
And then do the whole algebra.
That's as good of an expression as any. Integrate by parts and then do the whole algebra thing. The bring it over method. Right? How many times do you think we're going to have to integrate by parts? Twice. We have a sine. So when you see something like a sine, you should be thinking, well, if I integrate by twice, I'll get back to where I started. Yeah, so I defined I to just be the integral there. We can keep the negative if you want. Okay, we'll just put it in later. So I thought this is the more fundamental integral that we're doing. And so now when we integrate by parts, u is sine of x, du is cosine of x, dv is e to the negative tx dx. Or maybe it's actually nicer to keep them, well, it's not going to matter. And then v is going to be negative e.
I think we might want to do it that way.
No, this is fine. And then there'll be a 1 over t. Right, because I want to have a t dx. So I have to have a 1 over t.
All right.
I think it should be e to the negative tx.
Oh, e to the negative tx, yes. And now, when I do the boundary term, I'm going to have uv at 0. Well, sine of 0 is 0. And then as I go to infinity, that's going to be, no, so that's gone. And then I'll have the v du. So I'll have a negative sign from this. So we get I is negative integral from 0 to infinity cosine of x e to the negative tx dx, and I'll pull out the 1 over t. And now we just integrate by parts again. So u is cosine of x, du is negative sine of x.
Why did we? Can you say again why we got rid of the whole term besides that integral?
The boundary term?
Yeah.
Well, we've got uv at 0 and infinity. When x equals 0, the sine of 0 is 0. And then as x goes to infinity,
We're only going to evaluate it at those 2 points.
we're only going to evaluate those points because we're doing a definite integral, not an indefinite integral. Now we'll have to be more careful because on this one the boundary term will matter. As we get u du dv.
You can make cosine v now, or dv now, and then you can get it back. That doesn't matter.
Okay. Are you saying we should do it a different way?
Well, if you make u the e to the
Right.
negative tx, and you make dv cosine x, then v is going to be sine x, and you'll get a boundary term that doesn't matter again.
Right, but if I do that, if I make u be e to the negative tx, then I need to take the derivative of that. The t is going to come down, and I'm worried that I might actually just return to where I started.
Okay.
So if I try to do it that way, I think I actually return to how I start.
Okay.
So as a nice exercise, I suggest you try putting u equal that. It'll make the boundary term nicer, but I think you just return to where you started. And so we want to do it twice this way. So dv would be e to the negative tx dx. So v is minus e to the negative tx 1 over t. So now we get I is negative 1 over t. Now we have the boundary term. We have uv at infinity and 0. When I put in infinity, no problem, it's going to be 0. And now I have to subtract off what I put in x equals 0. Well, when I put in x equals 0, this is just negative 1 over t, and this is 1, so it's just 1 over t. Right? And now I have to subtract off v du, negative, 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 so negative integral from 0 to infinity of sine of x e to the negative tx dx, and I'll pull out the 1 over t. So we get I equals negative 1 over t squared minus 1 over t squared, I think I. All right, now we're just doing the algebra. And so we now get 1 plus 1 over t squared I equals 1 over t squared. Oh, negative 1 over t squared. So I'm a little worried about that to see if I made it. Oh, no, good. But we have another negative sign over this one. Fine. Okay, good. So we'll get, if I multiply through by t squared, I get t squared plus 1 times I is negative 1. So I is negative 1 over 1 plus t squared. So we get g prime of t is equal to 1 over 1 plus t squared. Does it seem reasonable that g prime should be positive. So I'm worried that we've dropped a minus sign.
I think when we're doing the first integration by
Right.
parts, it should be 1 over t instead of negative 1 over t before the integration.
Yeah. Because v is negative 1 for t and then negative.
Ah,
Yeah, because you subtract
Yeah.
v du.
Yeah.
okay, so over here,
Yeah.
Yeah.
Yeah, because you subtract v du
okay.
and the
So this should be a positive sign over here.
Yes.
Yeah.
Good. That should be a positive sign there. Good. So if that's a positive sign there, then that makes that a positive sign. Right? And then both of these become positive signs now? Or, no, this would be positive, and then this would be a negative sign over here.
Yeah.
So we had 2 minus sign mistakes, but they did not cancel. Good. All right. So this is now a 1 over t squared. This is now a negative. Good. So now when we come over here, we get, so we are, okay, so we did 1 plus 1 over t squared correctly, and then this should be a 1 over t squared. So now this becomes 1, so this becomes a 1, so this becomes a negative. So g prime of t is negative. Okay. Does it seem reasonable? So does it seem reasonable that g prime is negative? Yeah, if we go back to the integral, as t gets larger and larger and larger, most of the contribution is coming from that very first period. And the larger t is, the more you're decreasing the contribution. So it seems reasonable that g prime should be negative. This is why I was a little bit concerned at the end when we had g prime being positive. So we've now shown that g prime is equal to negative 1 over 1 plus t squared. Does anybody know a function whose derivative is 1 over 1 plus t squared? We may have mentioned that this semester. Arctan. So g of t is negative arctangent of t. Is that correct?
So why weren't we integrating dx, not dt?
I'm sorry? So g of t is the following. When we take g prime is just a function of t. The integration in x is executed. So at the end of the day, when we do the x integration, we are left with a function of t. And we have the nice closed form expression, g prime of t is negative 1 over 1 plus t squared. So does that mean g of t has to be negative arctangent of t? Plus a constant. Right? So what happens as t goes to infinity? What can you say about this integral? So get c by the limit as t goes to infinity. So when you look at this, what will happen as t goes to infinity? What will the integral become? It becomes 0. Because, if t is going to infinity, imagine t is negative a quadrillion cubed factorial. Once x is now ever so slightly positive, it's now hit by such an enormous number that this is now going to just bring this down to essentially 0. So as t goes to infinity, this integral goes to 0. Okay, what's the arctangent of infinity? Pi over 2. Right? So let's check. So arctangent is giving me what angle has a tangent of t. So this would be something like, t and 1. So the angle is going all the way up to pi over 2. So what should c be? negative pi over 2. Or just distributing the minus sign, hopefully it's arctangent plus pi over 2. And so let me just double check and make sure I haven't made any mistakes. Yep. I just wrote it as pi over 2 minus arctangent, but that's essentially the same thing. So we now know g of t is negative arctangent of t plus pi over 2. So what's g of 0? It's just going to be pi halves minus the arctangent of 0. What's the arctangent of 0? 0. So the answer is just pi halves. So this is a fundamentally new technique for integration, which you may not have seen before.
What allowed us to be fine with integrating the cosine x? Or I guess never mind.
Over here. For this part over here, when we were doing the integration by parts, we were fine because we have convergence because of the exponential decay. So this is related to a certain type of transform. I'll put some notes as to exactly which transform this is. This was a really good thing to choose. And so the question is, why was this a good thing to choose? It's a good thing to choose because we got a closed form expression for g prime. And with a closed form expression for g prime, we were actually able to integrate that and get a closed form expression for g. What happens is we have a 1 over x. By looking at something like a negative tx, when we differentiate with respect to t, an x comes down. And now we can integrate by parts. So the challenge here is figuring out what factor do you want to put in here. And that's the difficulty. And then you have to, of course, justify that you can interchange an integral and a derivative. And so I will post some stuff on real analysis as to when you are allowed to interchange a derivative and an integral. This is one of the big things we need to do in mathematics, is we need to justify these interchange. Otherwise, we become engineers, physicists, or maybe even an economist. Okay? It is often non-trivial because there are situations where you cannot interchange. What's nice is we have exponential decay. What you would want to do is you could look at the limit as h goes to 0 of g of t plus h minus g of t over h. And look at these exponential factors. And if you do that, well, what's nice is e to the negative t plus hx is e to the negative tx times e to the negative hx. And so you can begin to see how you would do it. Right? So for this problem, the interchange is not that hard. So I'll just sketch just a few little notes on that. And that's also one of the nice consequences of this choice, is you would look at g of t plus h minus g of t over h. And take the limit as h goes to 0, limit as h goes to 0. You'd have the integral from 0 to infinity sine of x over x, e to the negative tx, and then you would have an e to the negative hx minus 1 over h dx. And then what you could say is, well, once x is really, really large, this is going to be very, very small. So I don't really have to worry too much about large values of x. Over here, when I series expand, I can't series expand everywhere because I've got to be a little bit careful. But I've got maybe like the 1's will cancel, the h's will cancel, and I'll get something like nice like an x. So I'll have some kind of nice factor times this. Things will converge. And that really is, that's the x coming down. Right? We've got to be careful if x starts to get too large. I can't approximate this with a series expansion. But once x is becoming really large, I don't really care about what's going on here because I have so much decay, its contribution is negligible. So you've got to be a little bit careful with the bookkeeping. So let me give you another problem to look at. We've got about 5 minutes left. So essentially, this technique is differentiating under the integral sign, but with a twist. Is you have to figure out how to modify the original function. How many of you have read any of Feynman's books or stories? In one of them, he talks about how people would often come up to him saying, you know, I can't do this integral. And the people who came up to Feynman, these were people at MIT or Princeton. These are not, you know, integration novices. So what Feynman would say was, okay, look, they must have tried all the standard techniques. If the standard techniques would have worked, they would have tried them and they wouldn't be coming to me. So I'm not even going to waste time trying any of that stuff. I'm going to just assume it fails. Most people don't know about differentiating under the integral sign. Let me just try that first. And he got a wonderful reputation of being able to solve integrals that no one else could do really quickly. Because he knows, well, who's giving me this problem? So let's look at the integral from 0 to 1 of x to the 5th minus 1 over log of x dx. Let's say for some reason we want to integrate this. Go for it.
Is log of x base 10?
Base e.
Base
So what's your first concern? Does it converge?
logs of 0 are concerning, right?
Logs of 0 are concerning. And so the question is it decaying at a slow enough rate that everything will be fine? Oh, sorry, is it exploding at a slow enough rate that everything will be fine?
I mean, log of 1 would be 0.
Log of 1 would be 0. So we have problems at both endpoints. As x goes to 1, this is going to the log of 0, log of 1, which is 0. But we also have a 0 up top. And it turns out that that will actually overwhelm this. As x goes to 0, what does the log of 0 go to? Negative infinity. We're not too worried about dividing by negative infinity. So that's going to be more than enough decay. So the only issue is what happens as x goes to 1. And so you just have to show that everything is well behaved. So I have no idea how to integrate this directly. We need a parameter. So one possibility is to try to put in another factor like we did before. Or the other is to play Sesame Street. Do you know in Sesame Street they have, one of these things is not like the other, one of these things just doesn't belong? Which looks a little bit strange in this problem. Log x, I would say, is not strange. Log x is a fundamental quantity you could have in integration. Yeah, the 5. What should I replace 5 with? T. So let's call a function f of t is the following. And now I want to use the exact same technique as before. Why am I happy? If I'm looking at this, I've done this enough times in my life to be able to see why I should be so happy. The 1 over log x was a problem. When you differentiate x to the t, what are you going to get? How should you write x to the t? X to the t is the same as e to the t log x. So when you differentiate x to the t, you're going to get a log x coming down. So we get f prime of t is the integral from 0 to 1. And now when I take the derivative with respect to t, the derivative of x to the t is x to the t times log of x. So I get x to the t, the log x cancels.
What happened to the 1?
I'm taking the derivative with respect to t.
Okay.
So the negative 1 over log x, there's no t dependence there. So well, instead of writing it as x to the t, all right, so this is the same then. Well, okay. So now the question is, this is what f prime is. Can you integrate this? So I will admit, you might have seen me pausing for like half a second. The book that I got this from uses alpha and not t. And for a second here I was thinking t is here, but t is fixed. What's the integral of x to the t? This is just x to the t plus 1 over t plus 1 at 0 and 1. So it's just 1 over t plus 1. So f prime of t is 1 over t plus 1. So f of t is the log of t plus 1 plus some constant.
What about the case where t is -1?
I mean, for things to converge, I probably want to assume, maybe t is greater than 1. And so I'll leave the rest of this for you to figure out what should you take for c. But now, again, if we take, limits, we should hopefully be able to figure out what we want c to be. And then if you just take t equals 5 at the end, you'll have the answer. So this is an extremely powerful technique. We'll do a little bit more of this next class. But
Can you use